It is. Maybe one thing I can say is I'm like, that's like the end of the year. But no, because you feel like that. Oh, wait. Okay, you don't get sick of it. If you don't do it, I'll direct them, you withdraw it.
Okay, let's go to page 1. Okay, so today we're talking about we're moving into the units where we're dealing with curve sketching. So, but in terms of derivative rules, we've learned the majority of the rules already. And really, derivative-wise, we're just going to be using power, product, quotient, and chain. And but then we're going to see some applications beyond just finding derivatives. So we're going to look at behaviors of graphs and using derivatives to help us gain information about slope-related data. So again, you guys have a class copy. So each day you guys will just pick up the class copy, but then at the end, you can just return it back. But if you have your own copy, then great, you can just write in it. But otherwise, please don't write in the classroom copy. So extrema represents max and mins. That just means maximum and minimums. So if I have a hill or valley of the graph, we call them relative maximum or relative minimums. We can also see the word local. So local just means that within its immediate region, it's the highest point. So local or relative max is just talking about that region's highest point, or a relative minimum is talking about the lowest point in that region. Again, if you guys need a packet, please pick one up. However, this point here is not only a relative maximum, it's a relative maximum because it's a hill of a graph. It's a point where within the region is the highest point. So we call that a relative max. But we can also call this an absolute maximum because over the entirety of the graph, it is the highest point. So we can also consider that as an absolute maximum. In this case, we have a relative minimum, but we don't have an absolute minimum. Absolute minimum will have to be a physical point that we can identify. If we think of it as negative infinity, then that's not a physical point. So in this case, there will be an absolute maximum, but there will be no absolute minimums here. Okay, now if I have a closed interval here, let's say we have endpoints at the instead of arrows. So in this case, this point would be considered a relative minimum because it's the valley of a graph. It's also the absolute minimum because over the entirety of the graph, this is the lowest point. Here, this is the absolute maximum because it's the highest point overall, but it's not what we call a relative maximum. A relative maximum would have to be something that is higher than points on either side. So it has to be a hill. So endpoints, at least for us, endpoints are not relative extrema. So again, relative max and relative min, think of it as hills and valleys of graphs. Now, if I have an open interval, that means it's a hole at the endpoints instead of a point. This point would still be considered a relative minimum and an absolute minimum. But here, there would be no absolute maximum because even though we get infinitely close towards this point, let's say this is a y value of 5, we can always pick a point closer. So if I pick a point 4.999, I could pick a point even closer by just adding another 9 to the decimal. So here we can get infinitely close towards that highest point, but we can never pinpoint a specific number. So if there's a hole, we get infinitely close to it, but we don't have an absolute maximum value. Okay, just so some definitions here to kind of go through. Extreme value theorem says if a function is continuous on closed interval, then it's guaranteed to have an absolute maximum and an absolute minimum value somewhere on that interval. So if I have a graph that is connected, it doesn't have to be a smooth curve, it just needs to be connected and it needs to have endpoints, then I'm guaranteed that either the endpoints or the maximum or relative maximums, one of them will end up being the highest point, one of them will end up being the lowest point. Okay. You could have shared absolute minimum or shared absolute maximum, but in terms of the highest point, right, this is the highest point here, that's the absolute maximum, and here we have the absolute minimum. If a function is continuous on the closed interval, then the absolute maximum or minimum will either be at a critical number. Critical number is basically where the slope is 0, or at an endpoint. So even without looking at the graph, as long as we know that the graph is connected and there are defined endpoints, then without looking at the graph, we only have to consider where the slope is 0 and where there are endpoints. And then if we compare all those y values by plugging into the function, we can decide what is the highest and lowest points on the graph without physically looking at the graph. So critical values are values in the domain of a function where the derivative of a function is either 0 or undefined. So let me just draw another quick example here. So if I had a graph that looked like this, I only have to consider endpoints and critical points. So critical points can either be where the slope is 0 or where the slope is undefined. But either way, we can pull this information from the derivative. And as long as we identify endpoints and critical points and insert them into the original function, we can use the function to tell us between these candidates which is the highest y value and which is the lowest y value. So our goal here today is, can we identify the highest and lowest points on the graph just relying on the algebraic expression and relying on the derivative and not having to look at the graph itself. And then finally, on this page, max and minimum values refer to the y values of the point. So when we talk about max and mins, we're not going to provide order pairs. We're just going to provide the y values at that point. Okay, next page. So remember with intermediate value theorem, we always had to make sure that we stated the function is continuous. Same thing here. Any theorem that we come across, it's always the same initial condition. Establish the function is continuous on the closed interval. If you have a polynomial, then you just have to state that it's continuous on the closed interval. You don't have to do any tests. If there's a vertical asymptote, you want to identify it and see if that asymptote is impacting the interval. If it impacts the interval, then we stop the problem and say function is not continuous on a closed interval, and we can't go further with the theorem. But if the vertical asymptote does not interfere with the interval, then we can say the function is continuous, and we can move on to the other conditions of our theorem. So we always have to establish that the function is continuous because we need that to be able to ensure that the graph has a max and min. Next up, we find the derivative. And if there's a numerator and denominator, we set them equal to 0, 7. And then we take those critical points that we find from f prime, and we insert them and the endpoints back into the original function, and we simply compare the y values. The highest y value would be the absolute maximum, on that graph. The lowest y value would be the absolute minimum on that graph. Okay, so here's example 1. F of x equals 3x to the 4th minus 4x cubed. We're trying to find the absolute max and absolute min. This is a nice polynomial. There's no denominator variable. This is going to be continuous, no issues, but we just have to make sure we state that condition. So all we need to say is our function is continuous. And make sure you state your interval from 0 to 2. Okay, next up. Oh, and by the way, on this unit as well, you get to use a calculator on the quiz test. Okay, so F prime. We know we're going to test the endpoints, so we'll come back to them, but we're going to find critical points. We want to find, are there any hills and valleys that we want to consider as candidates? So F prime, we simply go through power rule. So 12x cubed minus 12x squared. And if there was a denominator, we will set that equal to 0. But here, there's only a numerator, so we only have to worry about setting the numerator equal to 0. And then just finding your critical points. So factor your GCF out. And then look for your critical points. So I have 2 critical points. I have 0 and 1. These are hills and valleys of the graph that may end up being an absolute max or min. We don't care if it's a hill or valley. We just are going to use the order pairs to help us find the absolute max, absolute min. So we have 2 potential candidates, and we have 2 endpoints. Now, are we going to use every candidate that we find as a valid candidate? Where do they have to live? In between, in the interval, yeah. So in this case, 0 is an endpoint, so it's a duplicate. So we'll test 0, but we only have to test it once. So we only have 1 additional value. But let's say -1 showed up. The -1 would not be tested because we only care about the interval. If it's beyond the endpoint, that is not part of our problem. Okay, so now we're going to be taking the endpoints and the unique critical point and inserting them into the function. And we just want to look at what the y values give us. So if I plug 0 into the original function, I get 0. If I plug 1 into the function, I get 3 minus 4, which is -1. If I plug 2 into the function, I get 3 times 16, that's 48, minus 32, that's going to be 16. And then between these 3 numbers, that's all we need to consider in terms of the highest and lowest points on this graph. We don't have to rely on the graph, we just rely on these numbers. But our focus is on the y value. So we're going to say the absolute maximum value was the highest y value that we see. 16. So we just say absolute max is 16. And then absolute minimum is what? -1. Okay, so no ordered pair. We just want to look for the y values. Okay, the location is not that important. It's the height that we're looking for. Okay. And then with extreme value theorem, you don't have to state extreme value theorem. You don't have to do a because statement. As long as you work through your conditions, you're good. So that means you state the continuity statement, you find your critical points and your endpoints, and you test all the valid candidates, and then you make your conclusion. You don't have to worry about because statements or writing it out, a justification like how we did with EVT. We will have to do that for other theorems, but for extreme value theorem, your work is your justification. Okay, next up, x minus 1 to the 2/3. There is no denominator variable, and then this is not an even root, so we don't have any restrictions with the function. So this is safe and continuous. So we just have to make the statement, don't have to do any tests here. So just always start off with your condition. Sorry, f of x is continuous. You're always going to be testing your endpoints with the original function. So you know you already have automatically 2 candidates. And then we are looking for additional candidates from f prime to see if there's any other candidates that land inside the interval. So we want to find f prime. So what rule do we have to go through in this case if we want to find the derivative? Chain rule. Okay, so sorry, that's a 2/3 there. So bring down the 2/3, keep the parentheses, subtract 1 from the exponent. That's the outside derivative. Then multiply by the inside derivative. Clean up your f prime. 2 stays above, 3 goes below, and the parentheses go below as well. Now, remember, the way you find critical points is you have to consider both the numerator and the denominator separately. It's possible that you don't find anything on one side, and it's okay, but we want to just get into the habit of looking in both locations. Is there anything that's going to come from the numerator? No. If I said 2 = 0, there's nothing valid, so we can ignore the numerator. But the denominator is going to give us a critical value as well. So we're going to set the denominator equal to 0 and see what we get out of that. Okay, so algebraically, we'll divide by 3 first. Cube both sides. Solve for x. So we have a critical point, but is this a valid critical point for us to use? Why not? It's not inside the interval. So if something is outside the endpoints, then that means it's okay if we don't find any additional critical points. It may be possible that we're only testing endpoints, because if there's no critical points, at least we looked for it, but if we don't find any, then we know that these are the only candidates for max and mins. So don't feel like you're doing something wrong if you can't find any critical points. You can still go through extreme value theorem. It's just that now you only have 2 endpoints to worry about, 2 points to worry about to find the max and mins. So they go back into the original function, and we're just going to compare the y values. Oops, sorry, -1. I did this wrong. It's 1, sorry, 1 minus -1. Okay, -1 minus 1 is -2. -2 to the 2/3. -2 squared is 4, so cube root of 4. Meanwhile, f of 0 is 0 minus 1, which is -1. -1 to the 2/3. The 2 makes it positive, and then cube root of 1 is just 1. So we're just down to these 2 values here. Okay, between these 2, which one is the higher value? Cube root of 4, right? 1 point something, 3 numbers that multiplies before. It's gonna be like 1 point something. It's slightly larger than 1, so there's my absolute max. And here's my absolute min. Again, just focus on the y values. Don't worry about the y. Don't worry about x. Absolute maximum. Absolute max value is cube root of 4. Absolute min is 1. Okay, example 3, algebraically a little, derivative-wise, a little bit messier here. But there is a square root, there is a restriction, but between 0 and 3, we're safe because nothing between 0 and 3 will cause that to be negative. So we know our function is continuous. We should have to make it that condition out of the way. Derivative, it's a little bit more involved here. What do we have to make sure we go through if we want to find the derivative? Yeah. Product and chain. Yeah. So let me so we'll start with product since product rule has sees a wider, larger portion of the problem than the chain. So once I get the G prime, then I'm looking at the outside versus inside derivative. Outside derivative is 1/2 parentheses, so negative 1/2. Inside derivative is -1. Okay. Algebraically, a little bit more involved because I got to worry about combining these two into the same fraction. I may need to involve common denominators. So let me see what I have here. So I merged all this together. I try to clean all this up here. 4/3 times 1/2 is the same thing as 2/3. So 2x goes above. The parentheses goes below, and 3 stays below as well. Now, if I want to combine these into the same fraction, I need common denominators. My common denominator is the 3 and the 3 minus x to the 1/2. So now we got to balance each fraction. This old denominator is missing a 3 minus x to the 1/2, so I need to multiply at the top by 3 minus x to the 1/2. But the nice thing here is if I multiply two square roots together, I'm just left with 3 minus x. So 4 times 3 minus x, the radical goes away. Here, no changes, so I can just keep that 2x. So I get 12 minus 4x minus 2x, and that gives me 12 minus 6x. And now the nice thing about this derivative is that we have clear places to look for critical points. So the numerator will set equal to 0, the denominator will set equal to 0, and we'll see if any valid critical points come out of it. If we do, then we're going to include them as well as the endpoints to test against the function to compare and find the highest and lowest y values. So I'm going to set the numerator equal to 0, solve for x, get x equals 2. I'm going to set the denominator equal to 0. Divide by 3, square both sides. I get x equals 3. Okay. Do we have any new candidates that we want to use? 2. The 3 is a duplicate, so we were already going to test 3. So we're going to only test 3 points: 0, 2, and 3. They all go into the original function. Two next. And then 3. 3 minus 3 is 0, so that's going to wipe out to be 0 as well. Okay, so we only care about the y values, right? What's the highest y value that you see? A third. So that's the absolute max. What's the lowest y value? 0. That's your absolute min. So absolute max is a thirds. Absolute min is 0. Okay, so that's all we're doing today. We're just going to practice with these problems. So just to recap, you have to look at the function and can you establish the graph is continuous on the closed interval? If it is, then make that statement. We continue with the theorem. And then your next step, find the derivative, clean up your derivative, set the numerator and denominator of the derivative equal to 0 if it applies. And then make sure that all the critical points you find are valid critical points, that they land inside the interval. And then you're going to test your endpoints and then your valid critical points back into the original function. And then you're just looking at your y values. Highest y value is your absolute max. Lowest y value is your absolute min. Right. Okay, so let's go to page 3. Okay, so start with 19 and yeah, your homework will just be page 3. So whatever we finish, or whatever we don't finish will be but as you do your homework, make sure you write down the problem on a separate sheet. So when I check your homework, I can see the problems that you're working on. It'd be easier for me to check, basically. Okay, number 19 is nice because it's a polynomial. So polynomial, there's no issues. We know the function is continuous, but that just means we don't have to check, but we still want to make that statement. And don't just say continuous. Make sure you establish the interval. Okay, next up, find G prime. There is no denominator to worry about, so we only have to worry about the numerator equal to 0. Is that a valid critical point? Yes. So we're going to always test 2 endpoints and any additional valid critical points that we find. And they all go back into the original function. Okay, you can use your calculator if you would like. Sorry, these are all G functions. All right, try 21. 21 is another polynomial, so no issues with continuity, but just have to get into the habit of establishing that statement as part of your justification. And just want to keep reminding us that just because you find critical points doesn't mean that they're going to be valid. So make sure that whatever critical points you find, that you're always comparing them against the endpoints before you commit to using them as valid candidates.
The way that we write it, can you write like absolute max is that and then write like.
Sorry, yeah. So sorry, I indicated that the X value, but I think it's best if we just don't involve the X value so we don't get confused. So we can just always focus on the Y value. Yeah.
Okay.
I wrote it this way because I said that the emphasis is on the Y value, but if we just completely take out the X value, then we can just focus on just the Y value. And that's the way that AP exam is going to ask it as well. If they're asking for a max and min, they're asking about the Y value. So if we just focus on the Y value, we can just get into the habit of just never looking at the X and just focusing on the Y. So ignore the X. I'm going to cross them out. We're just going to say, just give the Y value. Okay, any questions with 21? Okay, try 23. Again, the only thing you have to worry about with continuity is if you see a variable in the denominator. That's really the only time you have to look for a hole or asymptote and see if it's actually interfering with the interval. But if you see a weird exponent or radical or rational exponent, I think for the most part, we don't have to worry about them. They're just, you just go ahead and state your continuity statement. I'll work through the steps for 23. Everybody good with 21? Once I get to f prime, I did common denominator, so I can clearly see my numerator and denominator. Because in this case, both my numerator and denominator has variables. So I'm going to set them both equal to 0 separately. And 1 and 0, 1 is a duplicate, so I was going to use that anyway. 0 is a valid x value. And then, so we'll test three numbers, -1, 0, and 1.
Yeah. It's pretty good.
Is there any issue with continuity for 26? If I set the denominator equal to 0, am I going to get any real number? So there's no real number that can cause the denominator to be 0. So we checked, no issue with continuity. And then what rule would you use to find the derivative? Quotient rule. And then once you find the derivative, make sure you look in both the numerator and denominator separately for your critical points. 28 though is 28. Is there an asymptote?
Yeah.
Yes. Where's the issue? Is this going to cause an issue for us?
No.
No. This is not inside the interval, so this also can pass the condition. So continuous. Yes.
For 26, if we set the denominator equal to 0, what if we get imaginary numbers?
Right. So imaginary number, but there is no real number that can cause this to be 0. So I think in this course, we don't, yeah, we'll treat complex and imaginary numbers. It's not part of what we do here. So we don't have to worry about it. So that if that's the case, we consider that not valid. So yeah, so technically, yes, the imaginary numbers can cause an x value to be imaginary for this to be 0, but for this course, we're only dealing with real numbers. Okay. All right, so I'm going to have you guys finish 26 and 28 later for homework. So it's homework tonight is just, I'll be checking page 3 tomorrow, and that's it for tomorrow. But let me do a practice problem for Friday's review. let me ask you this, do you guys want to do a cone problem or a shadow problem? Which one do you feel need? All right, we'll do cone today and then we'll do shadow tomorrow.
Oh. What do you think is oh, yeah, I'll do it. I was like, I didn't even notice. No, I didn't. Like, yeah, I'm so sorry. I'm like, I'm so happy. Yeah, that's like such a bad thing. Like, I don't even have to say that. It's just you. That's all.
Hold on, let me.
Yeah, now I have like.
Yeah, you had no idea what I did there. Yeah, I actually. Well, it would have been.
What?
Okay, all right, copy this down here.
Or wait. That's all I'm yes, right, it's a spot.
No, it's strategic because five. You cut.
Wait, I'm so curious. Yeah, I was thinking. Cool, but that makes sense. I'm trying to get some music one day.
Yes.
Only for. You need anything?
Yes, you have to.
It does give us a.
Or would you use that later? Let's make sure you use it now, right?
Okay, so this is the information that we have so far. We have the dimensions of the cone. We know that dVdt is -12 cubic feet per minute. We have the radius of the water level at the moment in time, but we don't want to use that in our proportion. We'll save that till after the derivative. And then ultimately, we're looking for dHdt.
It's first said the rate is.
That's fine.
Yeah, that's.
He asked me to change of the whether it's.
Yeah, I think the question said radius.
Oh, it did? My bad.
Instead of height.
No, it said, let's see, 10 feet across, right? 12 feet deep. Yeah, 10 feet across.
It's like, what we find, it's like one radius is 4.
Yeah.
We're trying to find the EVT stuff.
Exactly.
That's fine. That's what I'm changing the rate. Yeah.
Oh my god,
Doesn't get paid attention.
I think Boston did that with the ball.
All right, let me. So, let me read the problem again. The water is flowing out of the tank at 12 cubic feet per minute. That's my DVDT. Find the rate at which the water level is dropping. Looking for.
No,
I've already got DVDT. And the radius.
Oh, no. I'll give you context then. Yeah. You're right.
wait, put that, maybe put that 25.
So we're looking for DHDT. So we would like to get our equation in terms of H so that DHDT will just naturally show up in our derivative. So I'm taking my radius, replacing it with 5h over 12, and just trying to get my volume to be purely in terms of H. Power rule for the H, bring the 3 down, subtract 1 from the exponent, include the HDT. So let's look what we have here. We have dVdt to plug in. We have the HDT variable showing up, but what we don't have is we don't have the height of the water level. Now, the problem doesn't give us the height of water level, but they gave us something related. They gave us what? Radius, right? So how can we use the radius of water level to help us get to the height of the water level? Yeah, we have our relation equation that relates. So I can plug 4 in for R, solve for H. Once I solve for H, then I'm just plugging in the HDT. Okay, so your homework is just page 3. And then make sure you return the classroom copy packet. Thank you.
I should get all of that.
Yeah, it's 25, but then I brought down the 3 and multiplied it. Like I said.
Yeah.
So.
You guys are longer than that.
Yeah, we all. Yeah, but we, bro, I was awesome. People that sorry. And then I swear to know because I saw it and I wrote it down instantly. It was. But it's not it's all right. It's
Okay, thank you.
I literally saw him change the. I was thinking about it. I know, that's why it's great. I think, yeah, I thought it was. I'll tell the point and read it. I saw him. I saw it. I swear, that's.
Thank you, everything's fine.
No, this is going. This is going. I'm already lucky if I'm on. Yeah. When you do it, how do you ever feel like you're
Treat pi like a variable, just don't put it
Is it like negative? I got like negative to fix 2.5. You need that's just. I don't think.
Yeah, just pretend like pi is a variable and don't plug in the calculator. Yeah, I'll plug everything in here.
Are we allowed to use
Yeah.
Oh, yeah, this one's neck. So then we don't take quiz today.
Yeah,
I know that. We will leave quiz today.
Yeah, that's why it's no, alright.
So, yeah, leave pi out of it and it'll just show you, and then the pi just hangs out.
So you might, I would just do it.
Pi,
And then
divide.
That's yeah, me.
I studied oh well. Yeah,
Alright, all your flip sides.
You're saying much.
I know it.
You'll have a test happening today.
Hey, I'm like a comic.
Good luck.
No.
Yeah.
So.
I'll use the four function calculator. I'll keep it.
Okay. I just don't know.
It's just so much. As if your calculator has a case cover, take the case cover off and just put it under your desk. Or put it in your backpack, but either way, just leave it out.